Lecture on ML Type Inference. This is video number 7. We study type unification algorithm and its correctness proof, and then we summarize type inference problem of simply typed lambda calculus we have learned so far. Type unification algorithm U. This is the main topic of this video lecture. This algorithm is used in type inference algorithm PTS we have studied in the previous video. At that video, I mentioned, I think, that this algorithm was invented by Alan Robinson for automatic self-improving and has been used in various algorithms involving symbol manipulation, including type inference. The original presentation by Robinson is rather complicated, and especially it's cumbersome to prove correctness directly using that presentation. So to my opinion, the best and most elegant presentation of this algorithm, unification algorithm, is due to Gallier and Snyder. I think I mentioned this citation already in the previous video lecture. So the idea of Gallier-Snyder style type unification algorithm is to consider a set of type pairs as a system of equations of type variables and transform equations until they are all in a solved form, in this form, where variable equals some value. In the type case, type variable equals some type, with the condition, of course, that this this variable does not occur in tau. So notation FTV of tau means the set of all types occurring in tau. To achieve this unification algorithm in this way, we define a transformation relation of the following form. So this transformation system transforms pair of E, S to another pair of E prime, S prime, where E is the set of type equations to be solved, and S is the set of type equations already in solved form, this form, and defines the algorithm U as the function of this shape, right? So function U takes a set E of type equations and return either S or failure. And so this algorithm first set up this pair, given E and empty set, and try to apply this transformation algorithm until it terminates. And if it terminates with this empty set, this E part becomes empty, then it returns this S part, right? Otherwise means that translation does not terminate with empty non-solved equation. Then there is no unifier, so that it returns failure. So this notation is the reflexive transitive closure. That is, intuitively means unbounded repetition, unbounded iteration of this transformation. One comment about this transformation. This corresponds to the usual equivalence transformation in solving a system of equation over, for example, integers, right? So in this case, in usual equation solving, you do equivalence transformation like subtracting equal value from the both sides of a solve. So this transformation we are going to define correspond to those ordinary equivalence transformation. So transformation rules of type unification U. There are three kinds of rules. And before going to each of the rules, I note one thing. You use this notation, E union, this singleton, pair of singleton set. The intention of this notation is that you select one particular pair from this set. That is the intention, right? So now let's go through each of them. First one is the obvious one, eliminate a redundant equation. If the selected pair consists of identical type, then these two are already equal. therefore you don't have to do anything. So you just eliminate this selected pair and return or result of transformation is just rest of E and S. So this is the obvious case. The second rule, variable substitution, this is a major one, right? So if the selected pair is this form, t equal tau, then this is already in a solved form, right? So variable equal value, so this is already in a solved form. Under the condition, important condition is this one, t doesn't occur in tau. If this condition is satisfied, then this pair is already in a solved form. So in this case, you move this pair into the solved position, this position, and then you do application by making a singleton substitution. This one, singleton substitution, that substitute this type variable t with this tau and apply this singleton substitution to E and S and create this new pair and return. So this rule transform this way, right? There is one comment that so these three rules are intend to be a disjoint. So t colon tau, if this tau is t, same t, then t colon t is subsumed by this rule. So t colon t is processed by this rule. This rule has precedence over this one. So an implicit understanding is that this tau is different from t itself. Maybe different type variable. In that case, this rule apply, right? So there are two notes on this rule. First one is that if the find tuple, when find pair t colon tau, this tau contains t, then the equation, this equation, t equal tau, doesn't have any solution. So we stop, we terminate. We can't do anything, so we stop at this point. Second one, so there is a symmetric case, tau colon t. So this symmetric case is assumed to be given. So we don't make explicit different rule, but symmetric case is assumed to be also given by the same rule. So this is the second major transformation rule. Third one is a trivial one. I mean, this is also trivial, and this is the simple one, and simplification or decomposition. So the other possible case, other than this one and this one, is this one. Both are function type. In this case, this one equation of two function type is decomposed into two because in order for this equation to be true, the sufficient and necessary condition is that these two equations are true, right? So you decompose this one equation to component-wise two equations. So this is obviously equivalent transformation. So this is a simplification rule. These three rules are transformation rules of type unification. So we have completed the definition of unification algorithm U. Now next step is to prove its correctness. So before the correctness proof, I make one general comment. An algorithm is correct usually mean two things. One is the algorithm always terminates for any input. And second, the computed result satisfies the specification. The second condition is obvious, right? It's obvious requirement. But first condition is also important because it is trivial to construct an algorithm that satisfies only the second condition. For example, if you define a function which never terminates, then because there is no result, therefore the second condition is always vacuously true, right? So first one is also need to be verified. So in the case of type unification, which is defined in this way, so takes E and either S, return S or failure, and use this transitive closure relation. So in this case, we need to establish the following. First one is that U of E terminates for every input E of type equation. So one more comment, so one general comment, which a form of repetition, but nevertheless I make one comment. So if an algorithm is defined by a recursive function, which is usually the case, right? Recursive function on inductive closure. In this case, termination is obvious. Termination is by construction. It's guaranteed, so you don't have to show anything. This property we learned already on this inductive closure, property of inductive closure in second video lecture, I believe. However, in our case, in this case, this function is defined using this relation, which is the transitive closure of this one-step transformation. Transitive closure means that intuitively I already said that unbounded iteration, right? So there is no guarantee that this unbounded application terminates. So we need to show that any sequence of this form eventually terminates. Another way of saying that is that there is no infinite sequence of this form. So this must be verified. And then to correctness property, first one is corresponding to this branch, so that if U of E returns S, then S is the most general unifier of E. And the second branch, if U returns failure, then E has no unifier. These three conditions we are going to show. So termination of a unification algorithm involving transformation relation. In such system, there is a standard strategy to prove termination. That is to define a complexity measure on terms of the relation. In this case, relation transforms this pair, so we assign for each pair, possible pair of E and S, some measure. Measure is some value ordered by some ordering relation. So in this case, we define this measure. Measure of E comma S is the pair. First component is the number of distinct type variables in E. And the second component is the number of symbol occurrences of E. Right? So these two natural number, pair of natural number, ordered by the relation, this relation. So comparing two pair, this one is bigger than this if and only if either this first component is bigger or first component is the same and the second component is bigger. So this definition gives an ordering on this pair. This is called lexicographical ordering on lexicographical pairing or lexicographical ordering on pair. Right? So this relation, and I note that there is a minimum or smallest element of this measure. So that is 0, 0, right? Because this is the number of occurrences, number of variables, number of occurrences. So must be 0 or equal greater than 0. So 0 is the smallest element. This one is also 0 is the smallest element. So this 0, 0, 0 is the smallest element of this measure. And furthermore, we can show this property. If some pair transforms to another pair, then the input measure is strictly bigger than output measure. Right? So this transformation decreases this measure. And also there is a minimum element. Therefore, these two, there is a minimum element and this transformation decreases always this measure. So we know that therefore there is no infinite sequence. Otherwise, so because this is bounded, this is a minimum, and this always decreases. So, and any pair has a finite pair of finite number. So there must be some limit of this transformation. So this is the termination proof, right? So therefore, this U of E always terminate for any input pair. So this proves the termination of U. So we have done this first condition of correctness of type unification U. Now remaining two, we show some property that implies these two property in the following slide. The properties of this transformation we are going to show are the following three. First one is that if E and empty set become E prime and S prime, then this S prime, that is a solved form appearing in the sequence of transformation step. This S prime is always of this form, that first component is always type variable, and then these type variables are all distinct and do not occur in E prime or this tau 1 through tau n. So this property is easily verified by checking each transformation rule. So I skip the detail. So this is left for an exercise, which it is nothing difficult. So please check this property. So this first property and second property. So if this starting pair become this form, that is empty unsolved form and S, then this S is the most general unifier of this set, which is the same as S, right? This is again obvious because under this first condition, S is a substitution, and therefore a most general unifier of substitution regarded as a set of pair is itself, right? So this S itself is the most general unifier of this pair because this is empty. So S itself is a most general unifier of itself, right? So this is regarded as substitution, and this is regarded as a set of pair, right? So this is also obvious. Now third condition. This is a major condition of correctness. So if this E comma S one steps transform to E prime and S prime, then the set of unifiers of union of E and S and the set of unifiers of union of E prime and S prime are the same, right? So this property. The elegance of Gallier and Schneider style unification is that its correctness is cleanly and rigorously proved by showing this property, right? So we are going to show this third property. The third condition means transformation preserves the set of unifiers. So we show this property. For this purpose, we assume this relation. Another way of saying that is that we pick arbitrary pair satisfying this transformation relation and show that set of unifiers of this union and the set of unifier of this right-hand side of this union are the same. And proof is by cases of transformation rules of this transformation, right? So first rule is this rule. So you eliminate equal pair, identical pair. In this case, it's obvious because any substitution applied to tau and the same tau is obviously the same. And therefore, any unifier of this union, if and only if the unifier of this union. So elimination of this doesn't change the set of unifiers. So this is obvious. The next case is this rule. This is a major rule I said about this major transformation that eliminate this type variable everywhere and make this to be a solved position, right? So now in order to show that the set of unifier of this union and set of unifier of this union are the same, we show one property, right? So for any substitution S prime that satisfy the equation, right? So any sort of substitution that satisfy S prime applied to t and S prime applied to tau, this t and tau are equal. Then for any tau prime, S prime applied to tau prime and S prime applied to the result of substituting t with tau in tau prime are equal by induction on this tau prime. Then by this property we can show that for any equation E prime, S prime is a unifier of this set if and only if S prime is a unifier of this set. Now E prime is any set of type equation, so you can take E and S and then get the desired property that this transformation preserves the set of unifiers. So this is the second case. The third case is, right, this is trivial. In the case of this one, right, this decomposition, the set of unifiers of this one singleton pair and the set of unifiers of this two-element pair are obviously the same, right? So this, in this case, the desired property also holds. So this establishes that this transformation preserves the set of unifier. The property we have just showed implies this second property, second correctness property. U of E returned S, then S is the most general unifier of E. Let's check briefly that S returned in this case. Now we showed that set of unifier of this union and set of unifier of this union is the same, and S itself is the most general unifier of this union and therefore most general unifier of E, and so this property is established. And now the remaining this property we are going to show in the following slide. The proof of this property. So for the proof we assume that U of E return failure, then by the definition of the algorithm, one of these must be true. First one is that this E colon empty set become this shape and stop, right? T, and at some point this pair appears, T and tau, and T contains in tau. In this case, obviously, this pair doesn't have any unifier, and therefore E doesn't have any unifier, and algorithm return failure because this stop and this terminates and never go to the state where this first component become empty. So this is the first case of failure. Second case is two cases, but it's the same, essentially the same. So second case is that this becomes this shape where there is one equation of base type and function type. In that case, obviously, there is no unifier, and therefore, this E has no unifier. So this case is the same. So the failure case, in either failure case, there is no unifier. So this, we concluded this property, right? So far we have shown the detail of the correctness proof of unification algorithm. Now let's see some example of unification in this style, Gallier-Snyder style transformation unification example. So this example is taken from the textbook I wrote, that compilers, principles and structure, unfortunately only in Japanese, available in Japanese. And now I said before probably that I have some intention to make an English video lecture course of this compiler based on this textbook, and at that time I hope to make a lecture note in English available, but this is just a future plan, not yet done at this moment. Well, let's go back to the example. Now this example, this is a given equation, and set the solved part empty, and we start a transformation. This transformation requires to pick one particular pair. So in this case, in this example, I pick always the leftmost pair, in this case, starting with this pair. So this is a focused pair, and look at this pair, then this is already in solved form. And t doesn't occur inside of this, so we just move this to solved position and make one-point substitution. That substitute t with this type and apply this substitution to rest of the element, this one and this one, but there is no t, so nothing changed, and we keep this rest so that this pair becomes this one. This is the first step of transformation. We iterate this process. Next pair is this one, so this is a focused pair. Again, this is in solved form, so we move to this solved position and make one-point substitution. That substitute t1 with this type, this function type, and apply to everywhere else, so that t1 occurred here and here, so this t1 and t1 become t2 or t4, and then we get this pair. So this pair transformed to this one, and then we apply again to the leftmost pair of this one, and this is both function type, so we decompose into this two, and this solved form doesn't change now. And then pick the leftmost pair, this one. This is in solved form, and therefore move this to solved position and apply the substitution. That substitute t2 with t4, and t2 appear here and here and here, so these t2 become t4, and then resulting this pair. So now, right? So now this is a final one, that only one remaining. This is already solved form, so we move this to solved position and apply substitution. That substitute t4 with t3, so that everywhere in t4 become t3, right? t3. And now this become empty, so the algorithm terminates with this substitution, right? So this is worked out example, very simple, but worked out example of transformation, Gallier-Snyder style transformation. Now we summarize. So far we have studied type inference of lambda terms. So a type inference problem of lambda terms under the simply typed system, simple type system, as I called the implicitly typed lambda calculus. This type inference problem is completely solved by defining a function PTS, taking E and return either typing in case E is typable, and failure if E contains type error. There is no typing. So that this function, that compute a principal typing of E, satisfying the following property. If PTS of E returns this pair, then any instance, set of all instance of this typing, returned typing, this set, is equal to the set of all derivable typing of E. This set doesn't mention any PTS or something. This is just a logically defined set of derivable typing. And this set and this set is equal. Right? So and also one more property. If PTS of E returns failure, then E has no typing. So this is a complete solution to type inference problem. Solve any form of type inference problem. So there is an exercise. I encourage you to try. The exercise asks you to define an algorithm that determines a given typing is derivable, this holds or not. hint is, of course, you try to use this PTS and also try to check that PTS given some typing, then the given typing is an instance or not. That relation must be checked. In that checking, hint is to consider some countably many base types, right, and use unification algorithm, right. So this is a recommended exercise. So we end this lecture by giving some example execution of PTS algorithm. Of course, PTS algorithm is implementable, and this is a trace of execution trace of implementation given in the textbook I just mentioned, right? So obviously PTS can infer a principal typing of any lambda expression, including these, containing free variable, of course, right? So this is the term, f and x are both variables. And then algorithm will return this one and print the execution trace. So, right, so actually this code you can find somewhere on the internet by other supporting material of this textbook, but the explanation is in Japanese, so I hope to make some English explanation accompanying this code. Right. So this is the end of this lecture number 7 of unification algorithm and its correctness.